So, we were discussing about the criteria for the convergence of sequences, and in this process we have seen two criteria. One is the monotonic convergence criteria for monotone convergence sequence, but that monotone convergence theorem, which is a very wonderful result, which gives the convergence criteria for a sequence, particular type sequence which are monotone, either monotone increasing or monotone decreasing sequence. And another criteria which is general in nature, that if a given sequence is given, one can find the limit of the sequence, and if the limit exists, we say the sequence converges. If the limit does not exist, or goes to infinity or minus infinity, we say the sequence diverges. But you see, in both the cases, there is a in the first case particularly, there is a drawback in the monotone convergence theorem. The main drawback is that this result is only applicable to those sequences which are monotonic in nature, but the sequence may not always be monotone sequence. So, in such a case, the monotone convergence theorem is not applicable to judge the convergence of the sequence. And second criteria which we told, though it is valid for any type of the sequence, but in identifying the limit itself is a problem, is a difficult one. So, what we want is, will there be any criteria which can directly say the sequence, given sequence is a convergent one or divergent one without going for the limit, and this is given by Cauchy, and it is known as the Cauchy convergence criteria, and it is one of the important result which relates the convergence of a sequence of real or complex number with its Cauchiness. So, in fact, if a sequence is Cauchy, then automatically it will be a convergent and vice versa. Now, this is valid in case of the real complex numbers, but when we go for an arbitrary metric space which we have not taken up, then the convergence criteria obviously does not help there. So, they will be defined in a different way, the convergence of a sequence. Okay. So, we will go on, since we have restricted our study only for the real number or complex number. So, therefore, this convergence criteria is very much helpful in getting the result for a nature of the sequence which is convergent or divergent. So, before going with the Cauchy convergence criteria, what is the Cauchy sequence? So, we say first definition of a Cauchy sequence of real numbers. A sequence x n x, which is x n of real numbers is said to be Cauchy sequence if for every epsilon greater than 0, for a given epsilon greater than 0, for every epsilon greater than 0, there exists a natural number or positive integer, you can say natural number, say n, which depends on epsilon, such that for all m n natural numbers m n greater than equal to capital N, which depends on epsilon of course, the sequence of the terms satisfy the following condition. These terms of the sequence x n satisfy the following criteria, that mod of x n minus x m is less than epsilon. It means a sequence is Cauchy if a x 1, x 2, x n, this is a sequence of Cauchy numbers, a sequence of real number or complex number. We say the sequence is a Cauchy sequence if for every epsilon greater than 0. So, first you choose the epsilon, then corresponding to this epsilon one can identify a point x n such that when we take all the terms after this x n onward, the difference between any two arbitrary terms after x n will remain less than epsilon. The distance between x n and x m will remain less than epsilon. All it is in the epsilon neighborhood of one of the say m I fixed, then one of the point in this. So, they are very close to each other. The distance between any two arbitrary point after the certain stage capital N onward, the difference is very small or is less than the given number epsilon. If this happens, then we say the sequence is a Cauchy sequence. For example, if we look the sequence, say x n is say 1 by n, we claim that the sequence 1 by n is a Cauchy sequence. So, it means for any epsilon is greater than 0. So, because if we choose any epsilon, because let us pick up choose any epsilon greater than 0 first, then corresponding to this epsilon one can find a natural number, then corresponding to this epsilon to this epsilon greater than 0, one can find a natural number, say capital H, which depends on epsilon such that let us say H is such which is greater than 2 by epsilon. So, H will depend on epsilon, we can choose a natural number which is greater than 2 by epsilon. Then according to the Cauchy definition, this difference must be less than epsilon. Okay. So, if I choose m n greater than n, so if we take n and m a natural numbers which is greater than equal to h, we have 1 by n is less than 1 by h, okay, or less than equal to 1 by h, and but h is greater than this. So, it is less than epsilon by 2. Similarly, 1 by m is also similarly 1 by m, which is also less than equal to 1 by h. So, it is strictly less than epsilon by 2. So, these two are less than epsilon. Therefore, when we take the difference between mod of x, therefore, mod of x n minus x m when n m are greater than h, this is nothing but the 1 by n minus 1 by m, and by triangular inequality it is nothing less than equal to 1 by n plus 1 by m, but 1 by n is less than epsilon by 2 and 1 by m is also less than epsilon by 2. So, this is less than epsilon for all n m greater than equal to h. It means the difference between two arbitrary term of the sequence after this certain stage h onward is less than epsilon. So, sequence 1 by n is a Cauchy sequence. Okay. That is one. Now, what is the negation of the Cauchy sequence? The negation of, because that will be required, negation of Cauchy sequence. If a Cauchy sequence does not satisfy, if a sequence x n does not satisfy the Cauchyness, so what is the negation of Cauchy? Negation of the definition of Cauchy sequence. Negation of definition of Cauchy sequence. Sorry, definition of Cauchy sequence. The negation is like this. The Cauchy sequence says that for every epsilon greater than 0. So, negation will be there exists an epsilon naught, and this should there exists a natural number. So, we can say that for every natural number h, then for all natural number h, so there will be a natural number m and n which are greater than h and satisfy this condition. Okay. So, we can say the negation like this: there exist there exists epsilon naught greater than 0, a small number epsilon naught greater than 0, such that for every natural number h, for every natural number h, there exists for every natural number a, there exists say at least one n which is greater than h and 1 m at least 1 m which is also greater than h, such that the difference between the terms of the sequence x n and x m is greater than equal to epsilon naught. Okay. Then this will be a negation of the definition of Cauchy sequence. It means, if you want to show the sequence is not Cauchy, then this criteria must be satisfied. For example, if we take this sequence, say x n is the sequence like 1 plus minus 1 to the power n, this sequence. So, then we claim that the sequence x n is not Cauchy. This is our claim. It means this condition is not satisfied. So, let us pick up the epsilon naught. Okay. So, let us choose epsilon naught equal to 2. There exists an epsilon naught, we take epsilon naught. Then, since the sequence x n is such which goes to 2 if n is even and goes to 0 if n is odd. So, if we take the n as even and n plus 1 becomes odd. So, difference between these two will be 2, which is epsilon naught. So, in fact, then for any h natural number h, we can choose an even number n greater than h, and then m, let m is n plus 1, which is also greater than h. We get mod of x n minus x m is nothing but what? When n is even, the x n comes out to 2, and when m, which is n plus 1 odd, so it is 0, which is exactly same as epsilon naught. So, this satisfies the convergence negation of the definition of Cauchy sequence. Therefore, sequence x n 1 plus minus 1 to the power n, this sequence is not Cauchy. Okay. So, the significance of the Cauchy sequence is the significance of Cauchy sequence lies in the assertion, lies in the main theorem, in the assertion. The assertion is that a sequence is Cauchy, a sequence of real number x n of real numbers is Cauchy if and only if it is convergent. If and only if it is convergent. So, that is the main item, that if a sequence is Cauchy, then it has to be convergent, and if a sequence of real number is convergent, then it will be Cauchy. So, this is the main result which we will show it here, and that is why the definition of the Cauchy or Cauchy sequence plays the vital role in the set of real numbers, system of the real numbers. Okay. Let us see the first lemma, which he says which is used, say lemma 1. Okay. If x, which is x n, is a convergence sequence, of real numbers, then the sequence x is Cauchy, is a Cauchy sequence. So, this is the first result which we want to show, that every convergence sequence is a Cauchy sequence. The proof of this is very simple. Suppose limit of the x n as n is x, because it is a convergence sequence. So, limit will exist, and suppose this limit is x. Then by definition of the limit for given epsilon greater than 0, there is a natural number say n 1, which depends on say epsilon 2, such that if we take n greater than equal to n 1 depends on epsilon 2, then mod of x n minus x is less than epsilon by 2, let it be 1. Okay. Now, if we take if we take another number n 2, we take n 2 which is greater than or equal to say n 1 depending on say epsilon 2, and if we choose n and m greater than or equal to n 2, then obviously for this particular n 2 this result is also valid, because this is true for all n greater than n 1. So, if we take n which is greater than n 2, that will also be satisfied, because it is greater than n 1. So, it will be satisfied. Then we have mod of x n minus x m, apply the time this is less than equal to x n minus x plus x m minus x. Now, this is less than epsilon by 2, this is less than epsilon by 2 for all n m, greater than n 2. Then in that case, the difference between x n minus x m is less than epsilon. So, this shows that, but epsilon is arbitrary, any number we can choose. Therefore, it follows that the sequence x n is a Cauchy sequence, So, that is what we wanted to prove. Okay. Okay. Now, as we have seen that a convergence sequence is a bounded sequence, and we have seen that every convergence sequence is a Cauchy sequence. So, basically that we are going to show this also, that every Cauchy sequence is also bounded sequence. Okay. So, that will the next result is lemma 2 says that a Cauchy sequence of real numbers is bounded. So, the proof is just based on the similar lines as we have done it in case of real. So, what we do is we take the sequence x n, which is a Cauchy sequence. Since Cauchy criteria is satisfied, so applying the Cauchy criteria, you can date the sequence x n is dominated by a certain number after a certain stage, and for the remaining one finite sum take the maximum value. So, that is what. So, let x be a proof. Let us see the proof is. So, let our sequence x, which is x n, is a Cauchy sequence of real numbers. So, by definition, for epsilon, any epsilon greater than 0. So, if we take epsilon, let epsilon is equal to 1. So, corresponding to this epsilon, there exists a natural number. This is sign for there exists natural number h, which depends on epsilon. Epsilon means 1, such that for all n greater than equal to h, the difference between x n minus x h is less than 1, because m we can choose. So, m is h. So, anyway, this implies that the sequence x n is less than 1 plus mod x h for all n greater than or equal to h. By modulus, because if this is greater, then we can just take it, or less than greater than equal to mod x n, and then. So, basically this is mod x n. Mod x n is less than this. Okay. Let it be 1. And then further you choose capital M as the maximum value or supremum value of mod x 1, mod x 2, mod x h minus 1, and then 1 plus mod x h. We can also use the maximum. In fact, supremum I have not defined, because these are finite number. So, we can change this by a maximum also, maximum term instead of supremum, that is okay. We can also take this maximum. So, when you take the maximum of these two, suppose m, then what happens? All the terms of the sequence x n will be dominated by m, and this is true for all n. So, this shows the sequence x n, this sequence is a bounded sequence. Bounded sequence of real numbers. So, every Cauchy sequence of real number is bounded. Let us see the converse part, and converse part will prove the Cauchy convergence criteria, that is complete. So, what the lemma 3 says, lemma 3, or you can say every Cauchy sequence, every Cauchy sequence of real number every Cauchy sequence of real number is convergent. So, combining first and second, Cauchy sequence of real number is bounded, and Cauchy sequence of the real number is already we have seen a convergent sequence real number is Cauchy, and if we prove the Cauchy sequence, every Cauchy sequence is convergent, then we can go for the Cauchy convergence criteria. Okay. So, let us see the proof of it. Suppose we have a sequence x, which is x n, is a Cauchy sequence, let be a Cauchy sequence of real numbers, Okay. Now, this Cauchy sequence, by previous result, a Cauchy sequence of real number is bounded by lemma 2. If you see, every Cauchy sequence of real number is bounded. So, by lemma 2, it is a bounded sequence. So, by lemma 2, it is a bounded sequence of real numbers. And by Bolzano-Restas theorem says, if a sequence is bounded, then it must have a convergence subsequence. So, by Bolzano-Weierstrass theorem, by Bolzano-Weierstrass theorem says that there is a subsequence x dash say equal to x n k, x suffix n k of x that by Bolzano there is a subsequent x that converges to the some real number x star. Some real number x star. Now, if I prove that our sequence x n also converges to the same number x star, then result is complete. So, what is required to prove is that the sequence x n will also converge to x star. This is our problem to solve. Okay. So, let us see how to. Now, what is given? The sequence x n is a Cauchy sequence. This is given. So, since sequence x n is a Cauchy sequence, so by definition of Cauchiness, for given epsilon greater than 0, there is a natural number say n 1 depends on epsilon such that for all n and m greater than or equal to n 1, say epsilon by 2. Let us take the epsilon by 2 because we will need further epsilon by 2 n 1. We have such that for we have the difference between x n minus x m is less than epsilon 1. Let it be 1. Okay. Now, the subsequence x n k is a convergent subsequence, converges to x star. So, by definition again apply the definition of convergent sequence which has a limit x star. It means limit of x n k when k tends to infinity is nothing but x star. So, since the limit of this x n k when k tends to infinity is given to be x star. Okay. This is given, we have got it, is it not? So, by definition of the limit, we can say for given for the same epsilon, for epsilon greater than 0, which is the same epsilon, there exists there is a natural number say n 2, which is suppose greater than or equal to n 1, which depends on epsilon by 2, such that n 2 and such that this n 2 where n 2 greater such that this n 2 belongs to this set n 1, n 2, n etcetera. This set means we are choosing the positive integer from a sequence n case. So, there exists a natural number n 2 from this set which is greater than equal to n 1 such that mod of x n 2 minus x star is less than epsilon by 2. Because this is difference of this can be made as small as we please. So, when k is sufficiently large it goes. So, we can choose the n 2 which is in this case greater than n 1. So, that this condition is satisfied. Second. Okay. Now, consider and this is true for what? This is okay, this less than s. Now, further this n 2 is greater than equal to n 1, which depends on epsilon by 2. So, from 1 the result is also valid when you replace m by n 2. So, from 1 we can say the result mod of x n 2 minus x n is less than epsilon by 2 for all n greater than n 2 depends on epsilon by 2, okay, for all n, because m I can choose to be n 2. Now, consider mod of x n minus x star. Now, this is less than equal to mod of x n minus x n 2 plus mod of x n 2 minus x star, and then this will remain less than epsilon by 2 plus epsilon by 2 for all n which are greater than or equal to n 2 depends on epsilon by 2, because both the conditions 1 and 2 are satisfied by this. So, what is that? The limit of x n is also n, limit of x n and n tends to infinity is also x star. This shows the Cauchy sequence is convergent, because epsilon is arbitrary. Since epsilon is arbitrary, so once it is arbitrary, we say limit of this. Okay. Therefore, the sequence x n, which is x, is convergent. Now, this lemma 1 and lemma 2 and 3, if we combine this 1 and 3, if we combine, we get the result which is known as the Cauchy convergence criteria. Cauchy convergence criteria, and that is very important result. What this criteria says? A sequence of real numbers is convergent if and only if it is Cauchy sequence. It is a Cauchy sequence. Okay, and this proves the result. So, combined the lemma, say this lemma 3, every Cauchy sequence real number is convergent, and then lemma 1, that x convergent sequence of real number, then lemma 1 and lemma 3 will give. So, lemma 1 proves lemma 1 and lemma 3 leads the following Cauchy convergence criteria. Okay. Now, let us see few examples where we can use this Cauchy convergence criteria to test whether the given sequence is a convergent one or not, where it is difficult to identify the limits. For example, if we define the sequence x n, is suppose a sequence x n is defined as x 1 first term is 1, second term is 2, and there is a relation between the term after 2 onward, after second term onward, the relation is like this, that x n can be obtained as a average of x n minus 1 and x n minus 2 by 2, average of. So, after second term onward, third term will be obtained as the sum of the third term x 3 can be obtained as a sum of what? X 1 plus x 2 by 2, fourth term like this way. So, this sequence, this is 2 for, this is defined for n greater than 2. Okay. Now, this sequence, if we find out the x n's by simply choosing x 1 is this, x 2 is this, then x 3, x 4 and so on, then what we see that this sequence is basically all the terms of the sequence are bounded and bounded by 2, because that I think this result we have already seen in the first earlier one, because this is monotonic decreasing when n is odd or increasing when n is even, like that way. So, but all the terms cannot exceed by 2 and below it is always be greater than 1. So, it can be easily proved that all the terms of the sequence x n are lying between 1 and 2. In fact, it was shown earlier. Okay, by choosing decreasing and increasing odd terms and even terms separately, and they are dominated by 2 n. Okay. But it is not a monotone sequence, but the sequence is not monotone, but sequence x n is not a monotone sequence. Its even and odd terms are monotone. It's even n odd terms, but as a sequence it is not monotone. Some terms are coming down, then up and like this. So, as a whole the monotone sequence is not there. So, you cannot say the limit exists, because when you say it is monotone, then only the limit will be, you can say, dominated by 2, bounded, but here it is not a monotone sequence. So, you cannot choose anything about this. However, it is a Cauchy sequence. However, it is a Cauchy sequence. The reason is because if we start with this x n minus x n, say where m is greater than n, let m is greater than n, consider mod x n minus n. Now, let us see, this is less than or equal to what, x n x m x n minus x n plus 1, because n is less than m, then x n plus 1 minus x n plus 2, like this, and then our last term will be this. Okay. Now, this will be equal to 1 by 2 to the power n minus 1 plus 1 by 2 to the power n up to 1 by 2 to the power m minus 2. Why? The reason is because if we look this term x 1 by induction, one can show that mod of x n minus x n plus 1, this is exactly same as 1 over 2 n minus 1, 2 n minus 1. Okay. This can be same, and this is true for all natural number n belongs to natural number n. It can be tested for n equal to 1, for n is equal to say 1, what happen? Mod of x 1 minus x 2, x 1 is giving to be 1, x 2 is giving to be 2. So, it is basically 1, which can be written as 1 to the power 0. For n is equal to 2, if we take, then you take x 2 minus x 3, x 2 is 2, and what is x 3? X 3 from here is the average of, when n is 3, it is x 1 plus x 2 by 2, x 1 plus x 2 by 3, 1 plus 2 by 3, that is 3 by 2. So, this will be equal to 4 1 by 2, which is 1 over 2 to the power 2 minus 1. So, suppose this is true for n. So, suppose it is true for, it is true for n, true for n, then m, then what we get is we are taking mod of x n m minus x m plus 1, this is given to be 1 by 2 to the power m minus 1. So, consider now mod of x m plus 1 minus m plus 2. So, that will be equal to what? Now, x m plus 1, this is equal to x m plus 1 minus x m plus 2 if I write, then this is equal to what? X m plus 2. So, x n x m plus x m plus 2. So, m plus 1 by 2, and that is nothing but equal to x m plus 1 minus x m by 2, and that will be equal to, according to this, it will be half of this, half 2 to the power m minus 1, that is half of 2 to the power m, like this. So, it can be proved this way, like this. So, by induction we can show this result. Now, use this result here, I use this result here, and then once I use there, then you can take common. So, 1 upon 2 to the power n minus 1 if I take common, then you are getting 1 plus half up to 1 over 2 to the power m minus n minus 1. Now, this is the part of the geometric series. In fact, geometric series is 1 plus half square and so on, and infinite terms are there, where the sum is, if you make the sum, a over 1 minus all, that is 2. So, this is strictly less than 2 over 2 n minus 1, that is equal to 2 over 2 to the power n minus 2. So, what we get from here is, therefore, mod of x n minus x m is less than 2 to the power 1 upon 2 to the power n minus 2, and this is true for all n, for large n, when m is greater than or equal to n. Okay, that's one. Now, if I choose any epsilon, given any epsilon greater than 0, given any epsilon, if I choose n, if n is so large that 1 by 2 to the power n is less than epsilon by 4, and if we take m to be greater than or equal to n, then what happens? The mod of x n minus x m is less than, this entire thing we want less than epsilon by 4. So, basically it is less than epsilon, and this is less than epsilon for all m n greater than equal to capital N, some integers n. Therefore, this is a Cauchy sequence. So, this implies sequence x n is a Cauchy sequence. Okay. Once it is Cauchy, therefore, the sequence x n is convergent. Hence, without calculating the limit, one can go the sequence is convergent for it. Similarly, if it is not Cauchy, then one can show it is a diverging sequence. For example, if we take the sequence, say the sequence 1 plus 1 by 2 plus 1 by n. This sequence, that is a sequence h n, where h n is the sum of this. Now, we claim that this sequence is diverging one. So, obviously, if it is not Cauchy, then it will be diverging, because every Cauchy sequence has to convergent. So, consider this thing now, consider h m minus h n. Okay. When you take h m minus h n, then what you get? You are getting from here is 1 over n plus 1, 1 over n plus 2, and then 1 over m, where m and n, m is greater than n. and this result is true for all n belongs to capital N. Okay. Now, this one is the lowest term is 1 by m, is it not 1 by m. So, it is greater than, and total number term is m minus n is greater than this number, which is greater than say equal to 1 minus this is equal to 1 minus n by m, 1 by n. Now, m and n are our arbitrary number, because one can choose m and n in integers. So, I choose m n, choose m to be equal to 2 n. Then what happens, this is this h 2 n minus h n, this difference is greater than half, and this is true for all n greater than capital N after a certain stage. So, this sequence cannot be Cauchy sequence. So, the sequence is not Cauchy, h n is not Cauchy. So, once it is not Cauchy, it means the sequence h n is not convergent. So, it is diverging. That is what it is, and this is known as the harmonic series, which we will come later on the discussion for it. Okay. Now, there is another type of the sequence, which we call it as a contractive type sequence. So, contractive sequence. A sequence x n a sequence x is x n of real numbers, a sequence x n of real number is said to be contractive, is said to be contractive type or contractive sequence if there exists a constant c, where c lying between 0 and 1 such that strictly less greater than 0, strictly less than 1, such that mod of x n plus 2 minus x n plus 1, this mod of x n plus 2 is less than equal to c times of mod x n plus 1 minus x n, and this is true for all natural number n. Okay. This it means that sequence is like this, that if we take the difference between two consecutive terms of the sequence, say this difference, then this difference cannot exceed by the difference of the previous one, that is a c constant times is always be less than equal to some number which is less than this, because c is less lying between 0 and 1. If I take c equal to 1, then only it is equal. So, it is less than equal to 1. So, it keeps deep differences keep on reducing for that. Now, what this result says, which is very interesting, the result is every contractive sequence is a Cauchy sequence. Every contractive sequence is a Cauchy sequence, and therefore is convergent. Okay. Now, again we will use the similar type of tricks as we did earlier, that first you make this difference x n minus 2 and so on like this, prove it. In fact, to prove this thing, I just give the hint say that first you show this part x n plus 2 minus x n plus 1, this will be less than or equal to c times mod x n plus 1 minus x n. Again apply this. So, it is less than c square mod x n minus x n and continue this. So, finally, what we are getting is finally you are getting less than equal to c to the power n x 2 minus x 1. So, this is coming like now consider mod of x n x m minus x n, and when you break up into the parts mod x m minus x m minus 1 up to mod x n plus 1 minus x n, then substituting these values, and finally, you will get this thing will come out to be c to the power n minus 1 minus c m minus n divided by 1 minus c and then x 2 minus x 1, but c is lying between 0 and 1. So, this part will tends to 0 as n tends to infinity. So, it is a Cauchy sequence. So, Cauchyness. Okay, prove it. Now, there are only one result which I will show for the divergence sequence. This result is very useful for a diverging. Let x n and y n be two sequences of positive real numbers and suppose that for some L which is real belongs to A and positive we have limit of this x n over y n as n tends to infinity is L, then limit of this x n over n is infinity if and only if limit of y n is infinity. Okay. The proof is very simple. This is given. So, from 1 we say for given epsilon greater than 0 there exists an n such that depends on epsilon such that mod x n by n minus n is less than epsilon, but epsilon I choose to be L by 2. So, is less than L by 2, and if I open this way we get from here is half L is less than x n y by n is less than 3 by 2 L when positive get. Now, if we multiply by y n, then what happen? This implies that half L into sequence by n is less than equal to x n less than equal to 3 by 2 L into by n. Now, these are finite. So, if x n by n goes to infinity, x n will go to infinity. If x n goes to infinity, by n. So, the result follows. That is all. Thank you very much. Thanks.